नहीं अभी नहीं ठहर जाओ। औज़ुबिल्लाहि मिनश्शैतानिर्रजीम बिस्मिल्लाहिर्रहमानिर्रहीम अल्हम्दुलिल्लाहि रब्बिल आलमीन अर्रहमानिर्रहीम मालिकि यौमिद्दीन इय्याका नअबुदु व इय्याका नस्तईन इहदिनस सिरातल मुस्तकीम सिरातल लज़ीना अनअमता अलैहिम गैरिल मग़ज़ूबि अलैहिम वलद्दालीन आमीन। Assalamu alaikum, ladies and gentlemen. A very warm welcome to you. Good afternoon and Assalamu alaikum to all our audience on the Facebook and YouTube. Today I am privileged to introduce to you Engineer Azhar BHATTY, a very experienced engineer who is going to present a lecture on precast, pre-stressed concrete. A very brief introduction of Azhar BHATTY. He did his undergrads in 1980. Undergrad means BSc Civil Engineering from UET Lahore, and then he has almost 4 decades of experience in civil and structural engineering, and he has in fact a very diversified professional experience. At the start of his career, he joined Lucency, a very famous Swiss contractor, in fact one of the biggest of its time, and they were based in Switzerland. Azhar joined them there, and Lucency was the developer of a well-known pre-stressing system, VSL. Thereafter, Mr. BHATTY came back to Pakistan. He has been freelancing here and there, and finally he joined AZHAR group of companies, today where he is the director design. AZHAR group is the largest producer of precast and pre-stressed concrete structural elements in the country, producing more than 10 million square feet per annum of roofing systems alone. Besides, a comparable area of steel buildings is also produced by the group. So this was a very brief introduction of Azhar BHATTY, and inshallah whatever he will present today, I am pretty sure it will be very knowledgeable for you, and you will learn from Mr. BHATTY's lecture quite a bit. So now I invite Azhar BHATTY to take the podium and start his lecture. Please give him a good hand.
Thank you. Assalamu alaikum. So today's talk I have.
Would you feel comfortable more with the questions being asked during the lecture?
Yeah, alongside. I mean, it can go both ways.
Okay, he has allowed you to ask questions during the lecture. The official time of question and answers would be once he completes.
But I would suggest that if there is a question without the answer of which you think you cannot proceed forward, you ask it there and then. But if you think there is a question for which there would be some extended discussion, that should be left to the last session for which we have allocated time.
Okay,
Thank you.
Okay, thank you. So today's talk I have organized into 4 sections. The first part would be the genesis part, and in the genesis I would like to talk about how pre-stress came into being. The limitations, the materials available at the time, the limitations of the material, and the people who developed them, and so on. And at the end of the genesis part, I would like you to indulge me because I want to touch on 2 topics. Strictly speaking, these are off topics, but I think they stem from this genesis and I would like to put them before you. In the second part of our talk, I'm going to discuss the methods of prestressing, the materials and their characteristics which are required for prestressing, the behavior of a prestressed concrete, ACI stipulations and regulations, and then you have, from the construction point of view, the various stages of prestressing, and then when you would discuss the stages of prestressing, then obviously you also come to the losses in prestress. In the third section, I will show you some applications of the prestressed precast concrete in our local industry, the various sections that we are using, maybe a comment on their characteristics. I mean, this cross section is behaving like this one is like this is the strong point of one section, the other points of other section, and so on. And finally, I have wanted some time for discussion. If somebody wants to make a contribution, give a personal experience, ask a question, pass a comment, and so on. So let's begin. So these are the traditional materials which were available before prestressing started. And if you take concrete, and let us say we don't define concrete as something which has cement as a binder in it. The binder could be lime or gypsum even. And so some people say that concrete was there when the pyramids were made. I don't know, maybe it is true, maybe not. But certainly by the year 200 BC, the Romans were using concrete. And as a binder they were using gypsum and lime. Hydraulic lime was in the 18th century, and the Portland cement came in the 19th century. The characteristics of concrete would be that it is strong in compression and weak in tension. Not only it is weak, the tensile strength is about, say, 10%, and it is also not very sure at what stress it is going to break. So the variance in tensile strength is a lot. Until to date, we don't depend on the tensile strength of concrete. So if you had to use them in buildings, so what you had to do was to find a form where compression would rule. Predominantly, the structure should be carrying the loads in compression, and so you had these forms of arches and domes. And I have taken some example of arches and domes, and I want you to have a look at them. You see, this one is from Andalus in Spain, this one is Alhambra, this one is the Blue Mosque. There are also some other examples, like for example the Shah Jahan Masjid in Thatta, which is, I don't think many people would be knowing about it. This is the Roman construction, and we also have our own fair share of domes in Lahore with the Masjid Wazir Khan and Bachai Mosque and many Mughal monuments. I mean, just keep in mind, I have taken these examples from our culture, and this is, I'm going to talk about it or touch these things in my off-topic comments, one of when we get over there. The second traditional material that you had at the time was steel. The steel was already in 1500 AD. You had these furnace, which was blast furnace, which was producing molten steel. Before that, perhaps we had only cast iron and wrought iron things. It was initially used as secondary elements. It was not used as a primary element. It was used as a secondary element, as connectors, straps, ties, base for domes and so on. Its compressive strength is comparable to your tensile strength, but the disadvantage is it is expensive, it is subject to corrosion, and it needs a continuous maintenance. So these were the two materials and the strong points and the weak points. And then the first innovation, because you see you had got concrete which was strong in compression but weak in tension, and then you had steel which was strong in tension but suffered from corrosive problems. So if you would encase steel in concrete, so then you have solved for the tensile stresses, and you have also solved the corrosion problem of steel by encasing it in concrete. So the first innovation was reinforced concrete. The reinforced concrete, where the compression stresses were taken up by steel, by concrete, and the tensile stresses was resisted entirely by steel. So the material, when it was subjected to say bending, you had compression in one part and the tension in the other part, in the lower part. So concrete would crack, and then all the tensile stresses would be transferred to concrete, would be transferred to steel. So sometimes, you know, I'm sometimes very amazed. People complain and say, oh, the beam has cracked. It has to crack. I mean, it can't take any tension forces. So it is a characteristics of reinforced concrete. It has to crack. So when you put in, the disadvantage of this concrete is you have to pay attention to your crack width. And if your crack width is much more than what is it can sustain, then you have got durability issues. To reduce your crack width, because then crack width depends upon the strains. So then you have to keep a limit on the strain of steel. And so you can't use a very high strength steel. You have to limit on your steel stresses. And since part of the section would be useless, so you need a heavier section for concrete. The first association for concrete was named NACU. It was the National Association of Cement Users in United States, and it formed in 1904. And this was the predecessor of ACI, which it was renamed as ACI in 1913. And in 1910, it produced the first standard for concrete. It was a 14-page document. And as compared to today, you have got 318.19. It has more than 600 pages. Compare 14 pages with 600 pages. Life used to be simple in those times. Or it is much more defined nowadays. Depends on which point you want to see. So the second innovation of these two materials, of combining these two materials, came in the form of pre-stressed concrete. Because, you know, the engineers realized that we are not fully utilizing the concrete. It is cracked, and we are using perhaps less than 30% of the concrete. So if we could somehow use the full section, so then we would perhaps be saving on the weight and all the related issues. So they started, that was the idea of pre-stressed concrete. So pre-stress would be defined as you create a permanent state of stress within the body of the element. And this permanent state would balance the stress field which will come during service stage. So that is the basic idea of pre-stressing. So the pre-stressed beam, what it would appear as in comparison with the reinforced concrete beam, the reinforced concrete beam is going to crack, it is going to deflect under normal loads or full loads. Stress, there would be some camber when only the dead load is acting, and when the full live load is acting, the camber will disappear and it will become straight and you will be free from stresses. So here are a few examples of pre-stressing. And by the way, pre-stressing didn't start with concrete. You had your timber bridges, they were pre-stressed, then you had your steel bridges, they were pre-stressed. And this pre-stress was done before concrete was pre-stressed. So here is a few examples which is a non-concrete examples of pre-stress. You have got this rider on a bicycle, and the spokes of this tire are very thin. Have you ever wondered why they don't buckle? Because they are very cylinder. I mean, the reason is that you have got these spokes, and you must have seen they are tensioning these spokes. So you have got tensile forces within these spokes, and when you add some load on it, so it is going to be transferred to the top because it is connected at the top and at the bottom. In the bottom part, the compression will balance the tension. There would still be some net tension left in the spoke, so it will never going to buckle. And the top spokes, the tension will be increased, and it will then transfer to the rim and then onwards to the ground. So that is one example of non-concrete pre-stress. Then you have got wooden barrels. If you see books on pre-stressed concrete, they gave these examples in the start and tell you where pre-stress was employed. So this is a wooden barrel, and it is filled with fluid and it doesn't leak. Why? Because you see these joints are under compression. You have this one stave of the barrel, and these hoops are there. It is heated and then cooled down, so they are in a state of tension, and when they are in a state of tension, they impart compression to these staves. So this becomes a watertight joint. And then another example of pre-stress. Perhaps everybody of you have a phone, has a cell phone with them, and they have put in some sort of protection over it, which is of tempered glass. And what is tempered glass? Would anyone know about what is tempering and how it takes place? The glass surface has some surface irregularities. It is a part of the process. And when you have got surface flaws, so then it becomes very difficult for the glass to take tension. So the inner part of the glass, it has got no flaws, so it is better able to resist tension. So they do a heat treatment whereby the center part of the glass comes under tension and the outer layer of the glass comes under compression. That is also a kind of pre-stress. So when you have got pre-stress on the surface with the compressive force and then there is no net tensile force, so the glass becomes almost 3 times stronger. It is able to resist 3 times more load. Now coming back to our topic of civil engineering. Manier was a great professor. I'll talk more in detail about this guy. And he explained pre-stress in this way. Say you have a stack of books, and if you try to lift the books up, so you will find that one of these books will slide up and it won't work. But if you press these books together, this stack can convert into a beam and you can lift this stack. And if you have pressed it, if there is enough pressure, so you can put more books on it, right? So you can make a beam out of these series of books, and this is how he explained his pre-stressed concrete to his students. And when I was looking at it, and then I saw the segmental bridge construction. Here is a part of the segmental of the bridge. And here you see these are the shear keys, these are the holes for post tensioning, and they are going to, here you see these are these elements, individual elements, and when you have tied them through these holes, you post tension them, it is a beam. This is the same example exactly as Manuel explained to his students much before. So concrete is subjected to compressive stresses to counter, because it is weak in tensile, so you add compressive stresses so that it is able to resist the tensile forces. So what would be the advantage we would gain out of it? You see, it's a high strength material, so you will use less quantities and you will have less weight. It is economical. Actually, the reason for high strength material will come, I will come to that later. It is actually for pre-stressed concrete, it is more of a compulsion and less of a choice, because pre-stressed concrete won't function if you don't have high strength materials. So you have got a high strength material, less weight, so it is aesthetically more pleasing. You have got lighter section, you don't have bigger sections, so visually they are quite nice. So then the second part is the cracks. You have now eliminated or minimized the cracks, which would mean that you have increased your durability. So the entire section is now effective because you have got no cracks. The entire section is effective. It means to span the same distance you can use a smaller section, because now the entire section is effective. Then you have got a greater shear resistance. If you would see the ACI stipulations, if you have ever designed, the column's shear strength is more than your beam shear strength, because you have got a compressive force, and that compressive force increases your shear capacity. You have got your elements of the beam, you are pressing it together, so obviously the shear resistance is going to increase. When the shear resistance is going to increase, so there's many cases where the shear governs, especially for slabs, when the shear governs the size of the slab. And so if you have got a greater shear capacity, so you can use perhaps smaller thickness, and that will reduce your weight. When you transfer pre-stress forces to the concrete beams, there is a state of stress. We call this stresses at transfer. And these are normally higher in value than the stresses we encounter during services. So if a member has sustained the transfer stage, so it is bound to behave well during the final stage. So it is very seldom that a member will fail in the final stage. It's very seldom. So, not to be afraid, not to be overawed by this sketches. I was just showing the sketches to trying to walk in those footsteps of how pre-stress was developed. It is amazing to see that pre-stress actually developed from arches. And it was Freycinet who was credited with the patent of pre-stress, and he was working with arches, concrete arches, and pre-stress developed from there. So let us just see, this is not an arch, this is a curved beam, because I have removed the lateral restraint at this end. And say you have got apply a dead load on top of it, so it will create a bending moment diagram. Here you see the bending moment diagram. There is compression at the top and tension at the bottom. And the value is about, say, I think it's about 1200 something. Mouse is not working. Oh, now it is. So you see you've got about 1273 kip-foot moment which is there due to dead load in the center portion, right? So I've taken the same curved beams and now I've removed that dead load on top and I've tried to put in some lateral loads on this side. Here you see I had removed the restraint, so all the lateral loads will be resisted on this end, and so there is a compression force in the entire arch, and now the bending moment has reversed in direction. If you would see the previous one, the bending moment was on the lower side, and if you see the next slide, the bending moment is on the now you have got tension at the top and compression at the bottom. And say I've just put an arbitrary value of that much. So this is the bending moment I get, which is about a little bit higher than the bending moment I got from dead loads. And if I add these two loads together, so from 1273 it is now dropped down to 232. It is now only about 6 times lower than what it would have to be designed for had we not introduced those lateral forces. I've called this thrust, but actually it is pre-stress. Now let us come to your live loads. You add some live loads on top because these are the permanent loads. The thrust and the dead load is the permanent load. And this live load can come and go, and this live load creates a bending moment, say, of 637. These values are arbitrary. This is just to demonstrate the principle of thrust and how it affects beneficially this curved beam. So if you had got only a dead load and a live load, so without any thrust, so you would have ended up with a bending moment of 1900. And when you take with the thrust and the dead load and live load, so then you have got a bending moment only of about 350. So from 900 to 350, so you have come again about 6 times lower. And this is more or less the basis of pre-stress. You introduce a force which will balance the force which is just going to come on it during service stage. So this is the early attempts of pre-stressing. So there's a person called Jackson. Jackson took out a patent for pre-stressed concrete in 1886. And Jackson, his family background, he was in a steel business. So really he didn't know concrete very well. So it failed. The reason is creep. So you can understand creep from this small sketch. Let us paint a blue dot on this steel strand which is in the center of the beam. And now you stretch this steel, so the blue dot will go to the right hand side, and then you lock this steel against the concrete. Over a period of time, the concrete is going to deform. It's called creep. If you remember the definition of creep, creep would be increase in strains at a constant stress level, constant strain level, constant stress level, yes. So that is the increase of strain, that is creep. So after some time, this thing is going to shorten. And the blue dot comes back to its original shape, to its original point. It means at this point of time, all pre-stress has been lost. So whatever advantage you wanted to take out of pre-stress is lost because of creep. So you have pre-stressing, then you have elastic shortening, and then you have creep, and all the pre-stress is lost. So he probably didn't understand the concrete behavior very much, and that's why this attempt wasn't successful. So this brings us to Freycinet. Freycinet, his background, just to give a little bit of his background, he came from a small village where he was friends with most of the craftsmen of that village, as was the time. You had a mason, you had an ironsmith, and so on. So he was friendly with lots of these people, and he himself says about himself that I was a very skilled craftsman. And then he went to the Polytechnic school in Paris, and then to the prestigious Roads and Bridges School, National School of Bridges and Roads in Paris. And he's the guy who understood creep quite well, because in his initial stage, this was as a bridge. This is a Verdura bridge, and here it is the introduction of pre-stress. This is the bridge. There was an old suspension bridge which was there before this bridge was built, and this bridge had timber stiffening beams, and it had to be replaced. The interesting story is that the village or the government of the area didn't have enough money. So they had money only for one bridge, and they wanted to make 3 bridges out of it. So as a designer cum contractor, he offered to make those 3 bridges at the price of 1 bridge. But then his condition was that you will not ask me what I am doing. I will not get approvals from you. I will just make the bridge, and if it doesn't work, then I'll make it again. So they agreed that they are getting 3 bridges out of the price of 1 bridge, and this is what he made. This is an arch bridge, and this is about 67 meters, the first span and the last one, and in the center it is about 72 meters. The arch is quite shallow. The span to rise ratio is about 15. When you consider that normal arches would say about be in the range of 5, 6, this is a shallow, very shallow arch, and it was in the range of span over rise ratio was about 15. This would mean that the slab would be under considerable compressive stresses. And he had a fair idea that concrete is going to creep. And this was a 3-hinge arch. Perhaps this one is better. This was a 3-hinge arch, so he had hinges at the top and bottom. And what he did was he installed flat jacks at the crown of these arches, right? And these jacks were then, they pushed these elements, these 2 parts of the arches against each other. In those days when you were making arches, this was called a decentering jacks. This is the arch, you push it against, so it is going to go up, and then you can decenter it, you can remove the formwork easily, and then you've got an arch. So he let the flat jacks in place. This one was made in 1910, and a few months later the arch were coming down, and what had happened was you had concrete compressive stress within the slabs or arch, and then you had creep. It means the arch was shortening, and if there's an arch and it shortens, it is going to come down a bit. The reason, then the next logical step would be that the compressive stress of the arch would increase, because now the rise is less, and so compression forces will increase. So if you don't attend to it, it is going to fall down. So Freycinet knew about this issue. He was a very clever engineer. He recognized it. And what he did was, I mean, if they would stop the traffic, then there would be panic in the society that this bridge is falling down. So at night, this is what he describes himself. At night, he used to take 4 or 5 of his trusted workers. They used to go onto the crown, and then they pushed the flat jacks which were there in place against these arches, and they raised the arch back to its original level. I mean, it was a very innovative of him to find a solution to save his bridge. I mean, there is a bridge which has got extra compression and it is coming down, and he induces more compression, but that compression was basically to lift up the arch, and he was able to save his bridge. But not for long, because World War II again came and this bridge was destroyed. So in 1928 he filed his patent for this pre-stressed concrete. He was a very innovative engineer, a very good engineer, but one was his language problem. He only could converse in French maybe, and he wasn't a very good communicator. So the pre-stressed concrete would have been then limited to the French-speaking part of the world. David Billington is a professor. He died recently. He is a professor at the Princeton University, also a very respected figure. If you know Billington, he has written a book on shells, and probably in my experience it is one of the best books on shells. And he wrote an article in the Portland in Pre-Stressed Concrete Institute in one of the journals, and he said that Billington said that along with Robert Maillard, he was one of the two greatest structural engineers of the first half of 20th century. Robert Maillard is a very famous Swiss engineer. He's a bridge engineer, and if you would see, there's a lot of praise for Robert Maillard. And from Freycinet himself, he said, the fields of pre-stressed and reinforced concrete beams have no common frontier. Either a structure is pre-stressed or it is not to be called pre-stressed concrete. So what I wanted to make I put this quotation because I wanted to make a point that despite his brilliance, he is not infallible. Now we accept cracks, we accept tension in the concrete, and it is still called pre-stressed concrete. So this is some of his works. You know, he has made beautiful bridges over here. These were light masonry bridge, and this is the first large span bridge that he made. It is the Astal bridge, and it has got a span of about 186 meters. It was a world record in arch construction in those days, and he gained an appreciation of the time-dependent behavior of concrete and things, of creep and shrinkage. Now this is the first pre-stressed bridge as we know it. This is the Lucency Bridge, and it has got a span of 180 feet. It's a box girder bridge, and it is a very cylinder bridge. It has got a span of 55 meters, and it has got a depth of 1.2 meters. It is a box section, and this gives an L over D ratio, which is a span over depth ratio of 45. This is a very cylinder number, if anybody of you would have an appreciation of these L over D ratios. It is a bridge which was made in 3 sections, and these are the box girder section. So this is probably also the first segmental bridge construction. And here he had to face this creep issues. So what he did was, if I could increase the size a bit. So this is the lower flange of the bridge, and he had installed jacks at the lower flange, so that in case of any loss due to creep, he could compress this flange even further. So if it wasn't for Gustav Maniel, pre-stressed concrete wouldn't have become a worldwide material, because he was known as teacher par excellence. It was perhaps his passion. He could converse very fluently without an accent in 3 languages. French was his mother tongue, but he could speak Flemish and he could speak English as well. And he was greatly respected. He worked in Ghent University. He was a director over there, a professor over there. And Billington writes that his design and research and teaching skills brought the knowledge of pre-stressed concrete to the English-speaking world. He conceived and designed the first pre-stressed bridge in the United States. It was the Walnut Lane Memorial Bridge, and this was in, I think, 1949-50. And actually, Pre-Stressed Concrete Institute was formed in 1954, and that is after this bridge was made. And this was Maniel. Being a professor, he had the training to conduct experiments, make observation, and make logical conclusion out of it. The same skill set was also available with Fressinet, because his teacher was at that time Rabot, and Rabot was the first lecturer on reinforced concrete. And as an influence on Fressinet, he had impressed on him that the importance of experimentation and observation. Unfortunately, in our scheme of education, we don't believe too much in experimentation and observations. We only believe in memory. You know, you memorize it and then you repeat it. So here I've given a few quotes from Maniel. It is just basically to indicate his level of understanding and how good a teacher he was. So he used to say, "You have got a big blackboard," and I used to write very long, complicated formulas. And I was so proud of myself. This is what he says. He says, "I was so proud of myself because I thought I was very clever." I mean, you require a lot of, how to say, inbuilt strength to say that I was wrong at that time. And he said, "Now I'm older, I have understood that writing complicated formulas does not solve any practical problems." This was his strength, this was his forte, to simplify things, to present them in a simple and a more understanding way. And then on testing, he said that you have to derive meaningful conclusions, so you have to test big beams, not toy beams. I took this diagram from the PCI journal, and this is an article. The article was written by Charles Solman, and this article appeared in May-June 1978. And Maniel died in 1955. So this was 23 years after his death. It means this piece of paper would have been with Solman for at least more than 23 years. And he retained this piece of paper, he treasured it, and in the end he made a photograph and he put it on it. What does that indicate to you? It would indicate, as I see it, that Charles Solman had a great respect for his teacher because he learned it from them. I would like to show you a few clips of Maniel because I was quite impressed, and luckily I found this clip from the Ghent University. And this is, you can see how revered he was from his students. This is Daniel going to give a lecture. And these are the huge boards that he was talking about. I have filled all these boards with complicated formulas. When I see this clip, I admire his handwriting and the way he's making straight lines and freehand and very legible. Billington used to say about him that his class was a mini United Nations. You had students from all over the world, and they would attend his lecture. And Billington himself said that I attended all his courses that he gave at Ghent University. And amongst one of his students was T.Y. Lin, because we are from the English speaking world and we only know T.Y. Lin. But T.Y. Lin was his student, and it was during this fellowship he got a Fulbright scholarship for 1 year. And during that time he wrote that book on pre-stressed concrete that we all know of. And Billington said that some of the students, he was giving lectures in 2 or 3 languages. And some students, they attended lectures in both languages because they were themselves bilingual. So, I mean, that was his attraction, you know, to the students. So if you study the body language, he comes out first and then the students just follow. So this shows a lot of respect that he had gained. This is from Ghent in about 1950, around 1950. So this is the first bridge that Manuel worked on. It is called the Longline Bridge, and it was made in 1948. And just imagine, in those times you didn't have a complete code of practice. There were no books which were available. So what he did was, he didn't design this bridge, he was in charge of planning and in charge of the project, you can say. And he converted this bridge into a full-scale lab because things were quite unknown. So he created this one. It's a box girder bridge. It is continuous over 2 spans. And it's got, I think, a span of about 67 meters, I think. So this is the bridge. It's a box girder. The bottom slab has been cast, and these are the walls of the box girder, and these are the strands which are coming. And somewhere there are so-called monitor wires. I come to that later. So these are the witness wires. I mean, he knew there's going to be creep, and he wanted to monitor the tension in the wires. So he put in these witness wires, and the thing was that these wires, when they are taut and you plug them, so they will vibrate and they will create a certain tone depending upon their frequency, and the frequency depends upon the tension in the wire. So just by hearing it, you could find out whether how much tension there is still in the wires. So this was the first structural monitoring, I think, of the pre-stressed concrete, just to see how much creep it would undergo. So this is the first bridge in North America. This is in Philadelphia. It's the Walnut Lane Memorial Bridge. It has got a span of, I think, about 158, 160 feet. The girder depth is roughly about 2 meters, and this is an I-section, series of I-section beams. And this was the first time that they made this post-tension concrete in the United States, and people were not very confident that it's going to work. So what Manuel did, Manuel was the designer of it. So what he did, he said, let's make a full-scale bridge, full-scale beam, and we'll test it to failure. And this is the picture of in those times they made a full-scale beam. It is about 49 meters long, which is about 160 feet. It was deep, 2 meters deep, and this was then tested to failure. And what I want to say, 300 engineers from 17 states and 5 countries, they came to witness this test. It was raining, it was a rainy day, it was in October 1949, and if you have been to the States, you will find that it is also a very cold day. So they stood in rain for the entire day to witness this event. This is the way that they were enthusiastic about learning new things and in concrete, and that's the way that's why you see in 1954 they started with Pre-Stressed Concrete Institute, and it is not very long ago, it's only about 60 to 70 years, the PCI has been able to publish a journal which comes in about every second month. Plus they have published a handbook, design handbook, and we are now in the 8th edition of the design handbook of PCI. From the first bridge in 1949-50 to date, about 55% of the bridges in the United States are of pre-stressed concrete. So that is the amount of progress that they have made in pre-stressed concrete. A small example, this is Manuel's inequalities, and this is basically just a demonstration of those times where when computation power was limited and people sought graphical means of making their work easier and quicker and more efficient. So apart from other notables, you see you get Fritz Leonard. He wrote a book on pre-stressed concrete, and personally he's my favorite. And he in that book, the first page gave 10 commandments of pre-stressing. And he's the one who said no, partial pre-stressing is also allowed. You can have some limited tension in concrete. Abels, he was from Austria. He is from Austria, and then during the war he went away to England. He was teaching over there. He died a few years ago. So you have T.Y. Lin. They made a substantial contribution. T.Y. Lin was again a student of Manuel, and his book gives a very good chapter on load balancing. It handles this topic very well. Then there's this guy Yves Graham, which is not very well known perhaps in our part of the world. He worked with Fressinet. Fressinet was never his teacher. He was a designer come contractor. And Yves Graham worked with him. And Yves Graham wrote a 2-volume book on pre-stressed concrete. And Fressinet wrote the foreword to this book. And in this foreword, he was very affectionate towards Yves Graham. And now we are almost at section 2, and now I want to touch 2 off topics. We have seen those domes and arches, and I said these domes and arches are from our part of the world, a lot of it. And I would like to narrate a story to you. It's my own personal experience. About 35 years ago, I was with a German psychologist. He was a doctor. He was in Lahore for giving some lectures. And I so happened I took him around to historical buildings like Pci Mosque and the Lahore Fort. And then we were talking and discussing. And you see, it is our want. We normally lament and we say, yeah, we have been left behind. The Europeans have progressed a lot. And we are really at quite a backward and underdeveloped country now. So he listened to me quite patiently. And then he made a very telling remark. I mean, I would like you to ponder on this remark. And he said, you see, there were master builders who made these buildings. I mean, they were very skilled in their profession. And he said, the genes of these master builders are still amongst you. I mean, just think about it. What he was saying was that whatever faculties these master builders had, you possess the same faculties. You have the same potential. How you use it is up to you. See, so this is the first lesson. I mean, very grateful to that German psychologist, because he said, there is no point in feeling yourself to be down. You just have to make an effort, and you'll get over there. You'll get over there. Nothing is then impossible or difficult. That is one part. This is the first point I wanted to make. The second point is, you see, I was telling about Manuel and the way he was revered by his students and how he treated his students. And then you had Fressinet, who wrote a very nice foreword to Graham book. And Fritz Leonard, if you see his book, he has dedicated his book to his teachers. His teachers were Emil Morsch and Otto Graf. Emil Morsch is the guy who wrote the first book on concrete, in pre-stressed concrete in 1948. And he dedicated his book to his teacher. Right? So the point I'm trying to make is that there was a relation of respect and affection between the students and the teacher. The teacher was very affectionate towards his student, and the students were very respectful towards the teacher. I mean, this is the only way that you can learn. I mean, I don't find that there's any other way that you can learn. It's the only way that you can learn. So this is, I think, one of the points that I wanted to make, that between the teachers and the students, there should be a respect and affection relationship. So that brings me an end to the section 1 that I want to talk about, and how it came about. So if you would, whenever any questions come to mind, please do come forward and tell me. So let us go now to the mechanics part of it. So pre-stress, as we classify today, you can classify it as when it is applied. So you have got, first part is pre-tension concrete. Pre-tension concrete is when you have got sealless tension before, and then you concrete later, and then release the steel and impart the pre-stress to the concrete. So the pre-stress is then stretched against bulkheads. So concrete is poured and gains sufficient strength. And pre-stress is then transferred through bond. Right? And this is known as Hoyer's effect, where the next slide will give you a little bit better view of what Hoyer's effect is. It is economical because no mechanical anchorages are required. Labor is saved because you have got normally a Longline method where many units are pre-stressed simultaneously. And it is suitable for industrial production. This is the predominantly in precast, pre-stressed concrete. So this is, here you see some few sketches. This is the Longline method. I mean, this is one abutment, the second abutment. You stretch the wires between these two abutments, you cast all your beams over here, and then you cut off these wires from here, and then pre-stress is transferred to this beam, to this one, to this one. So what would be Hoyer's effect? This diagram illustrates the Hoyer's effect. If you stretch a wire, you have got this Poisson effect. Poisson effect means that you stretch the wire, it is elongated in one direction, but then the diameter is going to shrink, right? And if you take the wire or strand, so this is the one where it is gained full force, and this is the end which this force is 0. This is the end of the beam. This will be somewhere here, and this will be somewhere here. So the diameter would be larger at the end, and it would become smaller at the end of the transfer zone. And this creates a sort of a wedge. And this wedge is then used, very helpful for bond. And that is how you transfer, pre-stress is transferred into bond. So this is, you see a view of the Longline method. You have got, this is the jacking end, there's a jacking end right at the end of this one. It's about 400, 500 feet long. So you cast 400, 500 feet beams, and then you cut them according to the stoppers that you have placed them. This one is if you would notice, perhaps you can see this is a protective grill at the end, because sometimes the wire gets broken and it comes out like a bullet. Should we wait for a couple of minutes for the... So that was the first classification, pre-tension, where steel is tensioned before. The next, I come to post-tension. Steel is tensioned after the concrete has hardened. So what would be the sequence? The sequence would be, you put up the formwork, put in the reinforcement, make the cages, then you place the sheath. The sheath is which will contain the tendons. Then you concrete it, and after it is cured and has gained strength, you place the tendons in the sheath, and then you jack against concrete, because concrete is now hardened, so you have got something to jack against it, and then you transfer the pre-stress to the end anchorages. And finally, when you have done with it, you have to grout the sheet to give it corrosion protection. So it is a complex operation because you have to do so many steps. You have to pay attention on the elongation part of it. You have to run a protocol because elongation perhaps is also important in pre-tension, but it is vital in post-tension, because then you have to see that if the stress has been transferred to the entire length of the tendons. So its area of application would be large elements which you cannot lift or transport or take to site. So if you've got a beam, say 300 or 400 feet, obviously you can't do a pre-tension, because how are you going to take it to the site? So graphically, this is, you have put in a hollow duct here, then you run the tendons through it, you pull it, and then you cut them, and then you've got a post-tension beam. Some pictures of it. These are the ducts. You see, you have to put in the reinforcement before, then you have to fix these ducts in position because they have got different profiles. Another aspect, you see these helical reinforcement over here. Could anyone guess why?
For resting to
Yes, it is for the anchorage zone. You're correct. Because when you enter, because these are very high stresses and they are introduced at the ends, and so this one is going to burst, and to cater for that bursting forces, you put in these helical ones. Another aspect is here is a slab which is post-tension, and this is the jacking end. So you have the cables coming out of here. But this end is the dead end because there is no cable coming out of there. So they have put in, this one is a U-shaped and with a steel sheet at the end to cater for that transfer of forces. This is the jack that you have multiple strands all at one time, and this is the operation procedure. You run the strands through the pressure plate, which is here, and which holds the wedges here. Then you put in the jack. The jack will stretch the strands and then push in the wedges. So this is the operation of post-tension. Some examples. This one was done in Lahore by us. So post-tensioning is possible. It is being done. This is the company I used to work for had made this kind of arrangement, VSL, one of the anchorage, and here you see this helical reinforcement. This is the pressure plate, this is the plate which holds all the wedges together, this is the duct, and here if you see this one, this pipe is for grouting. This is visible at this point because you have to introduce grout after tensioning to fill in this duct. This one is from VSL, this one is from Dividag. This is a German company, and you see more or less a similar sort of an arrangement. When I was in Switzerland, we had a symposium, and you see, you had put in wedges over here. These wedges were, because the metallurgy was perhaps not very well done, these wedges used to crack, and there was a complaint of cracked wedges, and then they had to redo their metallurgy, and finally they found a solution to it. So we have talked about pre-tension and post-tension. So the next classification would be whether you have a bonded system or you have an unbonded system. All precast pre-tension beams are bonded because the pre-stress is transferred through bond. So all these are bonded systems. The post-tension members that we saw, which was going through the duct, and if you grout the duct, then you also have a bonded system. For the same steel, for the same steel. This ultimate strength of a bonded system is a bit higher than that of the unbonded system, because your stress increases when it goes towards failure. The stress increases in the strands. In the unbonded system, the stress remains constant. It doesn't change. So this is your post-tension members where ducts and sheets are not crowded. This is the monostrand. You see, you have got only a plastic sheet, then you have a grease to protect for the corrosion, and this is your strand. This is your unbonded system. External prestressing, this is also another unbonded. Here you see, this is a box girder bridge, and you see these are external prestressing strands. I mean, it is not always disadvantageous to have external prestressing. What would be the advantage? The advantage would be it is easier to inspect. You can go over there and see how the corrosion issues are. If you want to strengthen it, it is easy. You can strengthen it. You can add some more strands in it. And if you want to replace a strand, you can replace the strand. So it gives you some flexibility if you have got external pre-stressing. But in a box girder bridge, it is easier to do because everything is then hidden from you. If you are outside, then perhaps it is not very aesthetic. So let's talk about the material part of it. These are the different stress strain curves for different concrete strength. You have normally a strain of 0.002 is to 0.0025. That's the maximum strain that you have. So what would be the properties of concrete that we would be interested in when we are using it in pre-stressed concrete? Compressive strength, obviously. Modulus of rupture. At what strength the concrete is going to crack? Because that strength will define you this, how much stresses you can put in, how much deflection it is going to give, and then how much would be the crack width. So we are interested also in finding out the modulus of rupture. The shear strength, obviously moments are not without accompanying shear. Your modulus of elasticity, which will give you your deflection calculations, and then you have got long-term creep and shrinkage. So these are the properties, primary properties which would be interested in. Of course, there are other properties which you can say is durability and things like that, but these are the primary properties that you are interested in as a pre-stressed concrete work. So the second part of the pre-stressed concrete is your strands. And what would be important over here? The ultimate strength, the yield strength, modulus of elasticity, and relaxation. These are typical stress strain curves of a grade 270 steel. And at about, I think, 0.1%, I think. Yes. This one. Here you have then, this is the yield strength of these strands. So let's look at these. Now we have got added 3 types of beams, and let us look at the behavior of these beams. You have the reinforced concrete, which is going to crack and deflect under dead loads and under live loads as well. You have a fully pre-stressed concrete, so it is going to show camber. You can see the camber is coming over here under dead loads. And under full dead plus live load, it is going to perhaps straighten up a bit more. There would be no cracks. Then you have a partial pre-stressed concrete. So normally it remains straight for dead loads, and under live loads, then it deflects a bit, there would be some cracking. So let's see where we should place the strands. This is a unreinforced beam. Obviously, we have decided that the concrete has no useful tensile strength. So when the moment would come and there's tensile stress in the beam, it is going to break. So the load carrying capacity for a non-reinforced beam from our assumption would be 0. It doesn't carry any load. Then we put in a strand at the center and we say we stretch the strand by a certain force P. And our limitation is that our maximum stress in the beam should not be more than 2P/8. Right? And when we keep that, we find that the carrying capacity of this beam is this much. It is 8Z/L square P/8. And now then we move your pre-stressing strand to your lower con point. So, and we have the same maximum stress level, 2P/8, 2P/8. We have the same pre-stress over here, same pre-stress over here. But we have just shifted the location of the strands to the lower con point. And our load carrying capacity has doubled from 8 to 16. So that would give you a fair idea of what would be the optimal placing of a strand. So you have got an I-beam over here. Under self-weight, you have got a compression and a tension over here. And this is the final stage as well. Then you add a concentric load at the center here. And this gives a uniform pressure over here. So your pressure increases and your tension reduces. And this is the state. In this state, really you don't have much of a capacity to resist any further loads. Now you add a eccentric pre-stress. So this is your stress distribution for self-weight. These two depict your stress distribution for post-tensioning. This is the axial part, uniform compression, and this is the moment part, which is P times E, which is the eccentricity at this point. So again, this would give tension at the top and compression at the bottom. It is in opposite direction to your self-weight. So finally, when you add them together, you have got a little bit of a compression here and a lot of compression in this zone. So when further load will come, so this compression is going to increase here and this compression will reduce here, so you have got a lot of capacity to resist any further applied loads. So ACI gives you 3 types of pre-stressing, or 3 levels of pre-stressing. You have got an uncracked one, and it has got a limitation that your tensile stresses should not be more than 7.5 Fc. This is your modulus of rupture. So if your maximum tensile stress is less than this, so you have got an uncracked concrete. And if your tensile stresses lie between 7.5 to 12, so they say this is a transient stage. And if it is more than 12, so this is a cracked stage. And then it gives a very nice table where it gives you what needs to be done for the different types of, different grades of concrete. I mean, I just shortened it a bit and I said the check of stresses is required for class U and T. So class U and T, check of stresses. And the check of strength is required for all classes. And here you can see the behavior is uncracked. It is a transition between cracked and uncracked, and this is a cracked section. And then if you take non-pre-stress, it is also already cracked. So what type of a section properties you are going to use? You can use gross section. You can also use gross section for the transient stage, even though it is cracked at times, but they allow you to use the gross section properties. In the cracked section, concrete, you have to use crack properties. So these are different, you can have a look at them when you look at the code. So now we come to the construction part. So there are 2 stages, 2 distinct stages for pre-stressed concrete. You have got the transfer stage and you have got the service stage. During transfer stage, you have got pre-stress. As soon as you apply pre-stress, the self-weight starts acting in opposite direction to the beam. You see, because the pre-stress is trying to lift the beam and the self-weight is trying to deflect the beam. So this is a permanent stage of forces into the beam. And in the service stage, the pre-stress loses some of its value because of losses. And then you've got superimposed loads, superimposed dead loads and live loads. So these are the two distinct stages in pre-stressed concrete construction. This brings me to the losses part of it. A lot of emphasis has been placed on losses, because it started from time when there was no concept of ultimate strength. So they were more or less restricted to your control of stresses, because in 1950s, stresses, the ultimate strength equations for concrete came in, I think, in 1971 or 77 something. So this is a nice diagram which shows you the different areas. You have got this part is because of concrete, and this low part is because of steel, right? This part is instantaneous, and this part is time dependent. So if you look at the concrete, the elastic shortening takes place immediately. It is an immediate one, it's instantaneously. Then you have got shrinkage, which is a material property of concrete, and then you have creep. If you look at these arrows, so this is actually the losses due to creep are dependent on the stress in concrete. So it is not an independent feature. It depends upon the stresses within. The stresses again depend on creep, how much loss is there. So these are interdependent things. Shrinkage, on the other hand, is material specific. It has got nothing to do with stress. It is material specific. Friction is only with post-tension. With pre-tension, it does not exist. And then you have got losses due to steel. You have got the anchorage set. You see when you have the wedges and you release the pre-stress, the wedges will slip inside. And this is your anchor known as anchorage set. And then you have got steel relaxation. In contrast to creep, creep is increase in strain at the same stress level. So your stress level remains the same, but your strain increases. Relaxation is a bit different from that. Your strain is there, but your stress is then less. So this is the difference between your creep and relaxation. This is a property of steel, and now we are using low relaxation steel, so it is quite okay. So I think I've explained everything. Okay, now let us see what are the losses. I mean, it is very difficult to predict losses. They depend upon your volume to surface ratio. It depends upon your relative humidity. It depends upon the temperature. It depends upon the stresses to which the beam is subjected. So really, strictly speaking, you can just only estimate. It is interesting to note, in 1958, there was an ACI ASC committee, 423, which is dealing with losses. And they just gave a figure of 35,000 PSI, take the losses at 35,000 PSI. Then we had the Pci Design Handbook. This was in 1980, I think, second edition. And it just gave a value of 22%. Take 22% long-term losses. Then subsequently, for some reasons, the American Concrete Institute has decided, no, calculate the losses. And they gave a lot of long formulas for that. I mean, what would be the effect if we underestimate or overestimate losses? On the ultimate flexural strength, which I believe should be the governing index, it has got little effect. Right? It qualifies this statement by stating if the tendons are unbonded, right? So that would mean that the stress in the tendons do not change. So if you've got your losses, so your stress in tendons will reduce. There's no way that stress can increase in the tendons. So your ultimate strength, which was dependent upon how much force the steel is carrying, would diminish. So that is what is meant by when tendons are unbonded. If your final stresses after losses is less than 0.5 FPU, this statement would mean that you have stretched your strands and then you have released it, and the effective pre-stress left in the strands is less than 0.5 fpb. So when the concrete cracks and the steel stretches, so probably you cannot reach the full level of steel stress, and so you will lose on your ultimate strength. What it does affect is your service stage. It will affect on your cracking load, it will have an effect on your deflection, maybe vibrations and so on. So the equations of pre-stressed concrete for shear resistance is the same as for reinforced concrete. There is no difference whatsoever. It is also interesting to note that in ACI, I think it was in the last chapter on pre-stressed concrete appeared in 318.11. And after that, there is no separate chapter on pre-stressed concrete. It forms a part of the stipulations written for reinforced concrete, so they really have stopped treating pre-stressed differently or as a separate entity. So you can calculate shear forces. Either you can use a simplified equations given here, or you can be more enterprising and calculate the flexural shear strength and the web shear strength, but these are very involved calculations, and normally we keep ourselves to this one. This is a typical shear capacity curve for a beam subjected to UDL, and this is also taken from the ACI code. And if you look, this line is 2 under root FC prime, as you can see from here. And this is the capacity that you have for reinforced concrete. At the ends, where your shear is maximum, so your capacity of concrete has also increased. PCI recommends calculating deflection using a bilinear behavior. Bilinear behavior would means you have a pre-cracking and a post-cracking zone. One would tell you this is the time when the concrete has cracked. So this deflection part is calculated using I cross. And once it has cracked, you start using I cracked moment of inertia. So I think we have covered section 2. And now let us come to the examples of precast, pre-stressed concrete that we have. So there are 3 major classes of pre-tension concrete that we have in our local industry. This is specifically now for our local industry. This developed first, the I sections, then we developed the double T, and finally the hollow core slabs. And then you can have special applications. These were reinforced concrete, but these were precast. So these are special applications just to cover them. So this is the I section. Here you see the I section 1. This was the first development. So this development was under certain constraints. You see these were developed, I think, in early 60s, where your handling equipment was restricted. You couldn't lift very heavy elements. So you wanted to make as light as possible. That was one constraint. The second one, at that time, it was the stresses part of it. Stresses were the controlling factors. Ultimate strength was not. And so the I section is very efficient as far as kern distance is concerned. The kern distance for a rectangular section would be d by 6, but it would be more than d by 6. This is the property of the I section. And then you had pre-stress at the bottom flange and some pre-stress at the top flange, so that the pre-stress, net pre-stress would be coming somewhere here. This was very popular, and still many government institutes are using it. It is perhaps one of the cheapest pre-stressed concrete roof that we have. A few cross sections. This is the load carrying capacity for various girders. This is the Longline method. I think we have seen this previously. Here you see these are the jacking ends. This is where all those anchorages are for the construction stage. this is the roof, typical roof. You have got these I-section girders and got your precast slabs over here. This one is a tray slab, this one is a checkered plate. Then you can have a plain bottom slabs as well. So this is the cheapest type of a roof that we have in our country. Now that brings me to the second part. This is a double T section. I read recently an article in Prestressed Concrete Institute, and they described double T as the iconic section in the American precast industry. So the size varies from 20 inches deep to 32 inches deep, and the width varies from 8 feet to 10 feet. It has got various lifting capacities and carrying capacities at around 35 feet span. The economics work out in our country such as I girders become more expensive and double T becomes more economical. If you see the double T section, you see the weight of double T is much more than the weight of the I section. The superimposed load on the I sections in comparison to its own self weight is much less. So it means that you can jack against bigger forces, you can make a more efficient use of your pre-stress, because then the superimposed load will be a small amount. But in I section girders, the superimposed load is of a bigger amount, so you don't use pre-stress very efficiently. So this is in the yard, where this is the bed of the casting bed of the double T's, and after you take out, you can stack them over here. These are quite long. If you see this distance between two columns is around 25 feet. So this double T would be around 70 feet long. Handling of the double T, this is through a gantry overhead beam, overhead crane, and you've got these lifting implements over here. Another interesting feature of lifting is that you need to have a safety factor of at least 5 for lifting. Because economics are very driving force over here, so we have normally a safety factor of 4 for the lifting equipment that we have over here, in the hooks and strands and so on. The second part is, this is the anchorage zone for pre-tension members, because the bond forms over here. So we have had to add some bursting reinforcement, the one you saw from the post-tension work, so something of that kind is added over here. The second part is that this beam deflects upwards. You can see perhaps a small camber over here. Here we have put in the battens, which is away from the end, but in real practice, this point would be supported to concentrated loads. So you have to pay special attention to your end conditions. So after you have to transport it to site, this one is a adjustable long span trailer. It is capable of taking 70 feet long double T to the site, and here you have got this adjustable length of the trailer. So the double T now has finally arrived at the site, ready for hoisting. So this is a single story building, and so you lift the beam and lift the double T and put it on the ledges or the supporting beams. Here is another one. I took this picture because this is just to indicate if you've got a multi-storied building. So your construction takes place in vertical sections. So you put in this double T, then you put in the double T at the top. If you would have a conventional construction, which would be normal cast in situ concrete, so you would have finished one level and then go up to the next level. So it is going in horizontal sections. So in precast, pre-tension, you go into vertical section, unless you've got a tower crane with a lot of capacity to take. The weight of these double T can go from 10 to 12 to 20 tons normally. Most of it is within the 10 to 12 tons range. So this is the finished one, finished all of a double T, and these are the light spires, but you can put in skylights here as well. And I think most probably these are skylights over here. A parking garage, because parking garage spans would be, say, typically 55, 56 feet. So this is a very suitable size for a double T construction. A view, and this is a double T structure, and then there's it's also the roof is being used for car parking as well. You can hang all your services under the double T legs. Oh yeah, this is an interesting picture. Actually, this is a testing of a double T. Many years ago, we had made a double T for some client, and he complained, your double T has failed. So we went, had a visit over there, and really it was showing signs of distress. So we decided to change those couple of double Ts. So we took off that double T, so you can see this is taken from the side. You can see the marks of bitumen all along the edges. And we brought it to our yard. And I asked AZHAR, the late AZHAR, if we could play with it. And he very generously said, okay, play with it. So we subjected it to a load test. We calculated this much is the load this double T should have been sustained, and why it has failed, why it has shown signs of distress. There were cracks and there was some deflection as well. So we loaded it, and you can see there's a lot of deflection. Even from this shot you can see there's a lot of deflection. I just blew up this part of the frame to show you how much deflection there is. These are all cement bags which have been placed on top of the double T. So this was done about, I think, 22, 23 years ago. I think it was 97 that we tested this one. So it was, this picture was taken just for personal interest. It was nothing, for no other purposes other than to have an insight on how the pre-tension beams would behave, especially if they are damaged. It is about 40 feet in length, and the deflection noted before it started failing was 8 inches. I mean, just calculate 40 feet span would be 480 inches, and if you have an 8-inch deflection, so your deflection is about span over 60, which is a very high deflection, and yet it remained intact. It didn't collapse, it didn't fail. The reason is that in double T you've got a very huge compression section. Concrete doesn't fail. In ice section, the compression side fails, right? So you have got a brittle failure. But in double T, it is almost impossible to have a brittle failure. And the crack width, this is about 7 millimeters thick crack. This was near a failure point. And then we lifted off the loads. The beam had, double T had marginally failed because the recovery was about 6 inches. Still it is substantial when you see that it was falling at 8 inches deflection. It was able to recover 6 inches. So that is another property of pre-stressed concrete, that it has got a chance to recover the deflections. Reinforced concrete does not have that much of a recovery possibility. And this is after you have taken off the load. There is still some residual deflection. It just failed. So it was just basically a test done to see how it would behave.
So what was the conclusion of that test? Really, a complaint from a client was justified and the double-T was
Yes,
really
it was justified because it should not have cracked in the first place. And we tried to rationalize it at why it had cracked. There were about 3 double T's, and there were a couple of reasons which we could identify which would have caused this. One was, the first thing we saw was the client had installed a false ceiling after the double T were placed. And what he did was he drilled at the low part of the rib. The low part of the rib carries all the strands. And if you damage the strands, then you have lost your pre-stress, you have lost your capacity. So maybe they didn't know about it and they damaged the strands because these were only 3 double T's. The rest of the double T's were all right. That could be one possibility. So that's why you had cracks and the diminished load carrying capacity. The second explanation that I could find was that perhaps the strand had slipped during pre-stressing operation, and then there was not enough pre-stress which should have been there. So if there is not enough pre-stress, so it is going to crack prematurely. So that was the reason perhaps that it cracked. So this,
basically a combination of both.
it could be a combination of both.
Misuse and
Yeah. So this brings me to the Holocaust lab. This is just a computer graphics I put in this image just to draw your attention towards this rib. This is the edge details of the Holocaust. You have got cores which are empty to reduce your weight of concrete, and then you have got this edge. Just pay attention to this edge and remember it. I'll come to it in the next few slides. So this is the production of the Holocaust. It is an automatic plant. Do you see any labor in it? So it is a very machine intensive industry. So there is just guy who is operating this extruder, and this guy is bringing the concrete. Holocaust uses a very stiff concrete because it extrudes the section. It vibrates and it extrudes. And if it wasn't stiff, so no way this surface is going to remain straight. It is going to collapse. So out of necessity, you have to use a stiff section. The process of producing hollow core is such that the ends are never properly compacted. So what we do is that we cut off the ends of the hollow core. So then you have got sound concrete in the rest of the bed, and after detensioning, you see the wires have been detensioned, you saw off the ends of the hollow core. Here you see another computer graphic, and this shows side by side 2 hollow cores, and here is the edges, and we grout these edges, and these edges are very strong. When you grout these edges, so that means that this hollow core cannot deflect independently of this hollow core. So whatever load you put on this hollow core will be shared by the adjacent hollow cores. Right? Differential camber sometimes comes in pre-stressed concrete. You can very easily equalize the differential camber. You can between the 2 hollow cores. You can put in a nut and a bolt over here, tighten it, then grout it, and then release the nut and bolt, and both the hollow cores will have the same geometry. Yeah, about the edges. You see, this is the lifting jaw of the crane, and this hollow core is supported by this nib. The entire weight of the hollow core is supported by this nib, and not in the full length, only part of it. So that's why I was saying pay attention to the nib. It is a very strong section, and the nib is enough to hold the entire weight of the hollow core. Here you see the same one, it is being lifted, you are stacking it, and this is the cross section that you have. So the transport to site, it is about 4 feet wide, so you can put in 2, on a standard 8 feet wide trailer you can put in 2. So this is now at the site. This picture just shows these are the dams. You dam up the core because we have to concrete it. Part of it is in situ concrete, and if you don't dam it, then the concrete is going to run into these hollow cores and you're never going to get a compacted concrete. That is one. The second is that you create keys, because concrete will go into here and you have got these keys which goes into the precast one and it holds it. So you have got edge details over here. So really, if you have got an earthquake forces coming in, so you have got the hollow core, it is tied in both directions. So the diaphragm action is there. With the double T, probably you need to put a screed, topping screed on top to attain the same diaphragm action. But with hollow core, it is quite conveniently done. So this is a steel frame building, a multi-storied steel frame building. It's a parking structure, and we have used hollow core for this parking structure. If you would look at this one, perhaps it is in the next slide, is there. Yeah. We have welded some steel bars on top of the steel beam, and this is a joint between two hollow cores, and then you concrete this joint, so you get a very good connection. Let's see another one. Yeah, here it is. You have placed the hollow core, you put in the screed steel, and here are these connectors between the steel beam and your cast in situ concrete. You concrete the whole thing and you get a very monolithic sort of a structure. This is the final shape that you have over here. The same hollow core, and now used in a concrete multi-storied building. A similar process, except instead of steel you have concrete in situ work of steel, of concrete. So this is the cast in situ concrete, which is the main supporting beam. You put in the hollow core over here. These are the stirrups which are coming out to form a bond with the topping layer of concrete. So here you have the hollow core. This is a triple height floor. So you just raise it and it's done. This is the finished part of it. Another application, you see, we have got, we do not have a standard pre-tension concrete beams for girders, for bridge girders. It is very sad. I think in this is part where we have to develop it. The AZHAR has a standard girders. They have got bulb T girders which have been given by various DOTs. We don't have that. So there came a client and he wanted to have a bridge over a drain. It was a 3-span bridge. Each span was about 50 feet, and he asked if he had anything, because he didn't want to have the formwork through the drain, because that would entail a lot of work, so he wanted to have a precast solution. We didn't have a standard precast beam for that. So this is the main beam which we normally use for in conjunction with double T. Here you have the ledge. The double T normally sits on this ledge, and this is the main pre-stress beam. So we use this one as the main bridge girders. If you would look at the details, this web is protruding out a bit. These flanges have been held back. So this web will sit on the transom over here. There would be a second stage concrete which would hold it in place. So this stringer would be held in both directions. It is going to be held in this direction because the web is then embedded into the cast in situ concrete, and the flanges will not let it move in the longitudinal direction. So in both directions it has been locked in position. And then you have these stirrups protruding up. We have left a certain bearing for the precast slabs. So the precast slabs can rest on these bearings. And here you see this one. These are the precast slabs which is resting on the bearings. The stirrups are coming out. Then you can put in your deck reinforcement. This is span 1, this is span 2. Then you concrete it, and then the end spans are done. Then the next middle span, the crane and trailer comes on this span, and then it can be easily be bridged. So this is not pre-stressed, this is precast. These elements are quite large. This is, I think, about 70 feet long or 66 feet long, about 20 meters, I think, if I remember correctly. And these are a number of pieces. This forms the cone of the silo. And to judge, here is the man who is standing over here and here. And this is the cone. And there are many pieces, I think there were 30 pieces or something like that. They had to be held in position and had to be fixed and stabilized before concreting. And this was one of his kind job that we have done recently. This is the element with its openings, and everything had to be accurately done. This is from a crane. This is a view from the crane, so it was really a massive structure. This is the precast transom. It is in one of the very congested areas of Lahore. And this is the BHATTY bridge. And say if we had made it in situ, as was foreseen in the original one, you would need some time to put up the false work, put in the formwork, fix the reinforcement, do the concreting, and then wait for at least 9-10 days for it to harden. So it means it would have taken a process of at least, I think, 30 days to do it. This one was done in about, I think, a couple of days' time. And so there was minimum disturbance to the traffic. So, well, that's the end of part 3. So now if you have your questions, your comments, most welcome.
How much maximum strength for concrete you have achieved practically?
Yeah, that's a good question. We have pre-stressed concrete. We are using a standard strength of 5,000 psi. But some cases we have used up to 6,000. Yes. That also brings me, I think I overlooked one point. When we said that we are using high strength material. Actually, it helps in our pre-stressed concrete. But actually it is also a compulsion. Because you see, we have to deal with creep. We have to take into account the losses of strain which will happen. So if you have got a normal strength steel, it will not stretch as much. So you need to have especially high strength steel which will stretch more and can cater for the losses which will take place because of creep. That is one. And if we increase the strength of concrete, so that means the creep will be less. So actually it is a compulsion to use a higher strength concrete in pre-stressed concrete. Yeah.
So why don't we move toward ultra high performance concrete? Overall in the world, like in Japan and Canada, they are moving toward the ultra high performance concrete.
Yes, that's the next line that we should be thinking about. Yes.
Strength more than 200 MPa,
Yes.
20,000 kg.
Yes.
So that really decrease the steel and also pre-tensioning.
Yeah, but we need to get used to it. We are in an industry and we need to produce this regularly, I mean, all the time.
Economy of
Yeah.
scale.
Yeah.
Definitely need an economy, a scale, a value.
Value of it. And also we need to be used to it. I mean, we are now used to producing 5,000, 6,000 PSI concrete for now 30, 40 years. And our procedures have been streamlined for that. Testing has been done for it. Now, if we can make it in a lab or on a pilot project, we have still to see how we are going to apply it. You see, and many of the admixtures for ultra high performance concrete are not easily available. So it is also an economical question of how much we are getting for it.
In laboratory, I think we have tested up to 12,000
Yes,
PSIs.
yeah.
But
he's talking about, I think,
on project,
he's talking about 20,000, 25,000.
PSI on one project only, and that was only.
So fiber reinforced concrete is in practice in Pakistan or it is
Yeah, I think I heard that at the Kartarpur opening, they have used a fiber reinforced precast architectural section, but not really structural section. No.
But sir, what are the limits on using the precast pre-stress concrete, especially with respect to the architectural and load taking? Like, I think we are limited to burdening the load of, especially with the upper stories. When we are using the in situ concrete, definitely we have a flexibility of use and liberty of adopting any geometries for the upper stories. Aren't we limited to certain geometrical limits and points of load, especially in double T and these pre-stress precast elements?
Yes, in a way, yes. Because you see, we have got these forms which are fixed in shape. So even double T, which is a very efficient form, has got a limited shear area capacity. So you cannot exceed that shear force. So that is one limitation. The second limitation would be you have got the size limitation. You can't have a massive element because then your lifting capacity would be restrained. Your handling capacity would be restrained. So these are the restraints which are there. As far as loads are concerned, in double T sections we have seen that it has the capacity to take a lot of loads. So we have designed it for say about 200 PSF, sometimes 300 PSF. But then we have to modify the width of the double T. It is almost the same as for reinforced concrete, but yes, we have got limitations, sheer limitations.
One idea when you are stating the example of that cracked double T's and redoing that this is an advantage which perhaps you didn't mention in your use of precasting, that if you are facing a partial failure,
Yes.
or something you want to change some part of the building, perhaps this is very difficult to do in the in situ concretes. Wherever in precasting, if you want to enhance the capacity of certain area of a building slab or beam,
You can do external pre-stressing. Yes. And there are certain bridges in Pakistan, they were failing. These were post-tension beam and then they did external pre-stressing. We ourselves have done external pre-stressing for cast in situ work. But then they are difficult because you have to work for the anchorages, you have to define the shape of your strands and so on.
I have a comment here. I think it is misleading to say that pre-stressed concrete has a disadvantage. Reinforced concrete, steel, every element would have a disadvantage. You cannot have arbitrarily good. This is my point. There is no disadvantage, particularly with pre-stressed concrete.
Yeah.
If you design for it,
after all we have constraints for
that is a constraint for reinforced concrete also. You can't put arbitrary point loads anywhere you want. There is an assumed UDL, which never is a UDL. So we are assuming that it's fairly well distributed.
So when this precast member fails or when they show cracks, so there is any system to rehabilitate them, or the only option is to replace them?
Yeah, as I said, you can replace, you can find a solution for it. You can reduce the load, that is one. You can strengthen it by external pre-stressing. You can share the load with you can put in a steel beam or a steel section to cater for the loads.
Another thing, we have witnessed there are different types of precasting and pre-stressing in the first phase of metro in Lahore and the second phase of metro, that is Orange Line. There was different type of transom and different types of girders used in both metros. Would you please give a quick brief on that, how it was different? That was the first project, this was the second project, and there are use of technology as well.
Yeah, actually, I'm not fully familiar with what kind of differences were there, but I know for once the Orange Line girders are pre-tensioned. They are not post-tension. They are pre-tension. And if you would look at if you remember the Walnut Lane Bridge that I showed, it was a post-tension structure, and it was replaced. It was the iconic American beam, but it had to be replaced because of the corrosion issues. did not put in enough or good quality grout, and the strands started corroding, and they had to replace it. And it was replaced by a pre-tensioned concrete member. So pre-tension has got a lot of advantages in that way. Corrosion protection, long life, and things like that.
One comment on that, perhaps in the first metro, precasting and pre-stressing, that was an option, especially the transoms. But in the orange line, I think that was a choice and that was compulsion, and that was a pre-built part. And the first thing, perhaps the local industry was not confident enough for doing such a large and heavy precast elements.
Yeah.
And then in the second line, this was a purpose built. There were 2 factories for the transom and all that.
They had seen it happen once, and they said, look, there's a lot of advantage of doing it. Let's do it this way.
Yes.
You had a...
Yeah, I don't have a question. I
Yeah,
want
make a
to,
comment.
Just make 3 quick comments which could have led to some confusion, especially amongst the younger people. One, that reinforced concrete became possible only with the advent of Portland cement. This is what you must note. Before that, all attempts at reinforcement, introducing reinforcement into concrete were a failure at the Roman time. This is comment number 1. Of course, it was never said that it was otherwise, but just to clarify. Second, for Crete, there is a strain, but we must know that it is under constant load. So the loading is there, but the strain is increasing, although the loading is the same. You agree with this?
Yeah, I said about
Yeah,
that point.
That, but I think
About
there
Crete.
was some
Maybe it got overlooked. Yeah.
And the third comment relates to student-teacher relationship, and I am very passionate about it. I think this is one of the things that we have lost over the past 2 decades, and that has very badly hit
Our learning
the
capacity.
progress of the profession.
And this is the example from a European background. I mean, would you ever imagine such a relationship of
Eastern countries.
in Western Europe, that they would have such a relationship between the student and the teacher? This is one of the cornerstones of learning. I mean, really, there's no other way. So, thanks a lot.
स्पीकर के लिए भाई को कुर्सी तो एक ले आओ कहीं से.
ये कुर्सी का ये उठा.
Azhar Ali Bhatti, thank you very much. A very well presented lecture. And thank you very much all those who have watched this lecture on social media, that is Facebook and YouTube. We had about, I think, an audience of about 20 people there, though this time we did not get any questions from there, but I think the lecture was so interesting that the audience was pretty good on the social media. Before we start with the distribution of certificates, I have 2 announcements to make. Next lecture would be on 18th January next year, technically 2020, and it would be given by engineer Naeem Durrani, again, who is a very experienced and senior person, and the topic is temporary shoring system for deep excavations in an urban environment. It would be same time, 18th January 2020. And after this, I want to make an announcement regarding the committees. As you know, our 3 committees are already functional. That is a publication committee, application committee, and ethics committee. Now we have formed 3 more committees, which are overseas, lecture review, and I think the educational committee is also a new one. So I have put the notice on our WhatsApp and Facebook that any of our associates who would like to contribute in the committees, they can send their names via email, or they can call Mrs. Sadia Naveed and express their interest there to join the committees. So this was the second announcement. And the third one is again a request that please come forward, contribute in the committees, contribute in our publication, and propagate about PSCE so that we can get more associates and more student associates. At the moment, our strength is associates 132 and students are only 13 at the moment. So this is where we are lacking. So you people can also help in convincing your friends and also propagating about PSC. Let the people know what we are doing, the service which we are giving to the young and senior engineers. So these were the closing remarks, and now we will start with the certificate distribution. First, we will present the shield to the speaker, and Rizwan Mirza, can you please come and present the shield to the speaker, our guest speaker, Azhar Ali. चल भाई
Muhammad Abdan. Thank you. Hamza Halil. Thank you. Mubashir Bajwa.
Yes.
Thank you. Habibullah. Thank you. Muhammad Zubair. Muhammad Asharif Shahid.
Thank you.
Is it Asharif?
Asharif Sharif.
Okay. Muhammad Arshad.
Yes.
Okay. Rana Muhammad Ibrahim Ullah. Sadiq Raza Abid. Mr. Muhammad Tanveer Arshad. I request everybody to join the lecture on time. Otherwise, if you are significantly late, would not issue these certificates. Mr. Muhammad Khatib. Mr. Muhammad Hamza. Mr. Zishan Ahmed. Fatima Hanif. Hassan Majid. Muhammad Usman. Muhammad Abdul. Ahmad Hussain. Mr. Gulrez Khan. Sayyid Mustafa Ali. Thank you.
Thank you.
Mr. Arif Ali Khan. Mr. Muhammad Hassan Malik. Hassan. Mr. Zainul Abidin. Mr. Faisal Gulzar. Mr. Muhammad Lukman. Mr. Zishan Manzoor. Mr. Yunus Aziz Khan. Amina Siddiq. Mr. Muhammad Danial. Danial. Mr. Muhammad Imran. अपने नंबर चेक कर लें, किसी और एक नाम से एक से ज़्यादा लोग भी हो सकते हैं. Mr. Zafar Iqbal. Zaha has left. You are there. Thank you. Thank you all.
Before I close this session, I just forgot to appreciate what AZHAR said about student-teacher relationship. I'm really happy to hear what he said. And again, I want to emphasize the importance of student-teacher relationship. I mean, this relationship definitely will help to learn the things in more detail and more deeply. One of the reasons why the education system is going down, the respect for the teacher and the bonding between the teacher and the student has almost diminished. So now you people are out of the university. I don't know how many of you will get the chance to study again, maybe for the higher studies. So don't forget this point. And in addition to what AZHAR has said, I would also like to say that there is another aspect why the education is going down, and that is that we have stopped reading the books. The teachers have started teaching from the notes, and the students have also found it very convenient, very easy to study the notes and then appear in the exam. So whatever you will get, you get the knowledge through reading, and once you read the book and some things you don't understand, then you get the urge of asking the questions. That has also diminished. This is I think, one of the major reasons why the quality of education or quality of understanding something has gone down. So please, make it a habit to read the engineering books and of your choice. When we were studying, there was a book foundation. We used to get cheap books from there. That foundation, National Book Foundation, it has done a great service for the nation and for the students. Now maybe it's not there, but now the replacement is net. You can get a lot of cheap stuff from the net, cracked things, and maybe even the genuine original you can also buy at competitive prices. So please read the books. Inshallah, it will help you. So the session is closed, and enjoy a cup of tea with us. Thank you.
18 or more, 18.